Hello, everyone. My name is Jens Stücker, and today I'd like to tell you about this idea, which I call the boosted potential. So we first came up with this idea when we were having problems with the halo finding in warm dark matter simulations. So warm dark matter simulation is a simulation where you put a suppressed power spectrum at small scales, which then leads the universe to form less small scale structures. So in the bottom panel, you see a warm dark matter simulation, which has been run within the n-body simulation method. And you see that it forms way less small structures than a cold dark matter universe would do. But at the same time, you still see that it forms a lot of these small regular structures in filaments. And those halos, they are not physical objects, but they're just numerical artifacts of the n-body simulation scheme. So during my PhD and also in the last years, I've been developing this sheet plus release method together with collaborators. And in this simulation scheme, one uses a way higher quality density estimate, which one infers by interpolating between particles in phase space to get this sharp density estimate. And then if one runs the simulation with this density estimate, one doesn't form these artificial structures. However, now here I show you the halo mass function in those two different cases, and you see that this friends of friends mass function seems to saturate around this half mode mass, but then it goes up again at small masses, for example, in this gray dashed line for this n-body simulation. However, also in this sheet plus release simulation, we didn't have any of these artificial halos, you still see an upturn at small masses. So to clarify this a bit, I'll show you here a few examples of the structures which are found at this scale of 5 × 10⁸ solar masses. You see that in the n-body simulations, these are these artificial lumps in these filaments. However, in the sheet plus release simulation, we still find structure at that mass range, but they are typically just overdensities in the outskirts of halos, and they don't seem to be at all what we would typically call a halo. So I picked out two examples, which I will show you several times during this talk. So the first one is a well-defined halo, and you see this density field. And on the right side, you see what subfind, which is a very popular halo finding algorithm, says should be the bound particles of this halo. And it says this is a well-identified halo. In the bottom, you see a misidentified halo where you see there's this density field and this filamentary structure, and the subfind says, yeah, this thing here should be a halo, where I'd like to disagree that that is a halo. So this made me think a bit about what should we call a halo. So, and I think there's roughly three different answers one might give to this question. So the most common answer is to say a halo is just an overdensity. And for example, one can put a density threshold, say something like the mean density in an object should be 200 times the mean density of the universe, and then it's a halo. And according to that definition, the thing on the left side is a halo, but also the thing on the right side, because you can have very high overdensities outside of halos. For example, in caustics, the density field can even diverge. So by that definition, the thing you can have such things, but I wouldn't want to call them halos anyways. So then another way of thinking about this is to say a halo is something that should also be collapsed in 3 dimensions. And by that definition, the thing on the left side is clearly a halo, but the thing on the right side isn't, because it just has collapse in 1, 2 dimensions, but in the 3rd dimension, it's still extended. It didn't have any shell crossing associated with that dimension. So the last thing one could bring up is to say that a halo should be a bound object, in the sense that particles which are inside of this halo, they're confined to a restricted region in phase space because they cannot escape the potential gravity well from the halo. But in the case of the filament, you might be maybe confined in 2 dimensions, but particles can move with their energy freely along the 3rd direction. And therefore, a filament is bound to a lesser degree than a halo. Now let's see what subfind would say about this 3rd aspect of being bound. So in this subfind halo algorithm and in many other halo algorithms, they work in the following way. So you take the density field, then you propose a set of particles. For example, you just select the overdensity by this friends of friends algorithm, and then you find this set of particles, and then you check whether those particles are bound. For this binding check, they use the self-potential. That means one just calculates the potential, the gravitational potential from those particles, and then you get this self-potential on the right side. Then one checks for each particle whether its kinetic energy is high enough to escape this potential well towards infinity, or whether it's too low so that a particle is confined to that potential energy well. And so according to this binding check, it seems plausible that this group of particles could be bound to this potential well. However, there's something a bit fishy going on here. And that's the following. So if I, on the left side here, I show you the self-potential and the self-force, and you see this is a convergent force field, like a well-defined minimum and so on. And the right side, I show you the actual force field from the simulation. And you see, this is not at all converging towards the minimum. This seems just to be like a very stable structure, and nothing is collapsing in the third dimension. I think the problem here is that the tidal field has been neglected because we ignored all the remaining mass in the universe in this self-potential binding check. So I criticize that this subfind or this self-potential binding check is a bit of is using this self-potential, which is a very constructed quantity. It's not related to our equations of motion in the simulation and so on. And it depends heavily on the friends of friends preselection, and it physically neglects external tidal fields, which can be important, like in the situation I just showed you. So the thing I thought when I realized all this is, why don't we use the global potential to define a binding check in simulations? And the answer is the following. If you plot the global potential, you just see nothing. So this is the same structure I showed you before. On the right side, you see the global potential, and you just see there's this huge gradient, but there seems to be no correspondence at all between this density field and the potential landscape. Looks similar for a halo, for example. Here you see a halo object, and you see the potential, like it has a very small minimum, but the extent of the minimum is way smaller than what you would see as the overdensity structure from the halo. And there's just this large scale gradient which completely messes up your potential landscape. So on the positive side, the global potential includes the effect of all particles, but on the negative side, it's completely dominated by large scale gradients and by things which are far away, and you don't see anything therefore. And I think this is the reason why there has never been proposed any structure finder which uses this global potential, although it seems like a more natural quantity than this self-potential. Now, I thought the following thing about this. So we have this large-scale gradient, and this large-scale gradient just means that all my particles in my halo are roughly accelerated with the same acceleration, and they are in a free fall motion. But also this large-scale gradient doesn't really change the internal dynamics of the particles. So maybe it would be more appropriate to switch to an accelerated frame of reference for describing these particles. So if I would switch to an accelerated frame of reference, like here, for example, then this would introduce an apparent force in that new system of reference, right? And this apparent force will basically utter itself as a gradient in this potential landscape. So therefore, like from this accelerated frame of reference, I have to add a global gradient to the potential, and I call a thus constructed potential a boosted potential, because it's the natural way of looking at the potential from boosted frame of reference. So let's look at how this would look in practice. So this is the potential landscape of something like the sun plus the Earth. So one very massive body and very low mass body. And then the bottom left, you see this in 1D. And you see that we have a very weak minimum with a very small persistence. And there's this large scale gradient totally messing up my potential landscape close to the Earth. What we do in cosmological simulations, most of the times just we say, let's forget about the sun, let's just look at the Earth and check its self-potential and see what things can be bound to it. Then you can, for example, define this escape energy, how much the particle needs to escape to infinity from Earth. And you would, but you would also could possibly arrive at a few wrong physical conclusions. For example, you could say, no, I can have orbits arbitrarily far away around my Earth, but that's not possible. And you see that very well in the right panel, which is this boosted potential I propose. So in this case, I just subtracted this gradient, which is just given by the acceleration of the sun towards the Earth, and then created this potential landscape. And one sees a few interesting things in that case. So close to this, to the Earth, right, the boosted potential looks almost identical to the self-potential. But then I go further and further away, and the tidal field of the sun becomes more and more relevant. And at some point, these potential contours start opening up at the critical energy level. And if you're then particle or a satellite on an orbit which has a higher energy level than that, you might in principle escape the potential gravity of your Earth and start orbiting on this around the sun instead. Now, this boosted potential, right, one could now also define a new escape energy, which would be then the difference between the minimum and the saddle point in this potential landscape. And this escape energy will almost always be lower than the self-potential escape energy, because the tidal field makes it easier to escape your halo or like your Earth or whatever than it would be without the tidal field. So in the case, now I showed this for the case of this halo object I showed you before. And you see that now suddenly this potential landscape, which didn't make any sense when I took the global potential, actually starts to make sense. You see again a well-defined minimum, and you go further and further out, reaching this critical energy level. And you see that almost all of the mass of the halo is very well contained within this critical energy level. And then you go beyond that energy level, you see that the potential contours are now opening up alongside the filaments, which means that it's way easier to escape this halo in the direction of the filament than it would be orthogonal to the filament. Now, if I show you the object which was misidentified before by the self-potential, where I had this well-defined minimum apparently in the self-potential, it turns out in this boosted potential, I don't see any minimum. I just see that my potential contours are closing orthogonal to the filament, but along the filament, I can just move freely with a given energy level. So you would not identify this as a bound structure. Now, I can, with this new notion of a potential landscape, I can also define a new binding check. And that one is very simple. So I just take my potential landscape and measure this critical energy level and call that the tidal boundary. And also can, for example, define the volume inside of it is the tidal volume. Now, all particles which have an energy higher than that energy level I would say are unbound particles, and particles which have an energy, so which includes kinetic plus the potential energy, right? Lower than that critical energy level, they can be bound to my object. Now, if I do this in practice, you see the following result. So in the top row, you see in the second panel, the particles which are bound according to the self-potential binding check of subfine. So just remember, there was first this friends of friends pre-selection, which makes a sharp cut in density, and then you check the self-potential and find these as bound particles. And the top right panel, you see the particles which are bound to this according to this boosted potential binding check. And you see this is a way smoother transition between unbound and bound than the subfine binding check. And now for these particles in the bottom case where we have this misidentified halo, I just find not a single particle being bound according to the boosted potential. So now this cleans up a lot of the problems we had with this halo mass function. So the blue one, the blue line shows you the friends of friends mass function that was diverging at small masses, right? But the green thing now shows you the mass function I would get by removing all the objects which are not tidally bound. Yeah, and then you see that it still gets flat at small mass. It doesn't seem to decrease, and I think that might be just because a lot of these objects are just halos which are about to form, which are not virialized, however, yet. And you can see this in more detail in this paper I cite down here. Now, one can also use this binding check for cold dark matter simulations. So here I just show you the mass one gets from this tidally from this boosted potential binding check and the y-axis in comparison to the mass M200b, which is the mass contained in the radius where the mean halo density is above 200 times the mean density of the universe. And you see that these mass definitions roughly agree on average with some scatter. More interesting is maybe to look at this extent of this tidal boundary in the spatial extent. So this is showing on the y-axis the volume contained within that boundary, and this dashed line shows you this in comparison to the volume contained within R200b, and you see that the tidal boundary is typically quite a bit larger than the R200b radius, which means that particles can still be bound outside of R200b. I think that's also consistent with results of people who looked at the splashback radius, where they, for example, find that a lot of particles can still be turning around way outside of this R200b radius, which we very often use for defining the extent of a halo. Another interesting aspect is the virial theorem from this new perspective. So here I define the virial theorem through in the most classical way, which is given by this virial, which is the product between force vector and radius vector, and in comparison to the kinetic energy. And so if particles are on bound orbits, so they cannot escape to infinity, then the expectation value of this virial and the kinetic energy should come out this factor of 2 on average. Now, if I take this expectation value over all particles which are bound according to this boosted potential binding check, then I find this top panel. And you see that typical halos have this virial ratio of 2, and there are some scattered around it, which means that not all halos are virialized, of course. However, if I do the same thing with but just taking the average over all particles which are bound according to subfine, then you find that this virial ratio gets now biased towards lower values. And I think that happens in the following way. So in subfine, it's more likely that the particle gets selected when it's close to pericenter, close to the when it's close to the halo, than if it's at its apocenter, where it's very far away from the halo. And that's just because it's more likely to not pass this friends of friends preselection in the very outskirts of its orbit. And now that means that you're more likely to find the particle when it's at a high kinetic energy, which then biases this ratio low. Then the final aspect I wanted to talk about is that one can also use this perspective to learn more about tidal stripping. And here I put a very simple thought experiment. So we just start with an NFW halo, and then we very slowly add a tidal field to it, and then we create this final state. And so there's two main effects which are happening here. So the first effect is that you basically remove all the particles which are above the energy level associated with this critical contour, and this kind of makes an energy truncation. And the other effect is that you have this internal redistribution of energies, which then leads to maybe some additional particles being lost. And so if one assumes that this tidal field is added very, very slowly, then one can actually treat this in the adiabatic limit, where this problem becomes analytical because actions are conserved. And so we have been writing an article where we exactly put forward an analytical model for tidal mass loss in this adiabatic limit, and one can learn a lot about the tidal stripping of subhalos, which are orbiting in larger objects. Unfortunately, I've run out of time, so I will just leave you with this summary slide about a few ideas in which cases the boosted potential can be interesting. If you're interested in this, just have a look at this paper, which has been published last year on MNRAS. I'm happy to take any questions, like in the sessions, but also over personal messages. Thank you. Bye-bye.